Okay, so welcome to 7.5, Quantitative Changes in Equilibrium Systems. And this really is sort of a pivotal lesson. So by now, let me see if I can remember that. Oops. By now, you should be able to calculate the equilibrium constant. So given the concentration values, what is the KEQ value? For example, that equilibrium law assignment you did was calculating the equilibrium constant. Calculating the equilibrium concentration when the value of KEQ is known, as well as the concentrations of the other reactants or products. Determine what is the direction of the reaction prior to establishing equilibrium. So if K is greater than 1, less than 1, or if it's equal to 1 at equilibrium. So then we are going to calculate the concentrations when initial concentrations and the equilibrium constant is known. That's one of the types of problems we're going to do in this lesson. Oops. And there's sort of a variety there. So if you printed the note off, you can see the examples are listed and they're called problem 1, problem 2, problem 3, and problem 4. So problem 1 and 4 are a little bit different than problem 2 and 3. 2 and 3 just has like a mathematical difference, not really a chemistry difference. So what we're going to do is I'll do a video for problem 1 and then assign work, do a video for problem 2 and 3, assign work, and then a video for problem 4 and assign work. I think that's best in these weird times to sort of split the lesson up a bit. Okay, so when you are doing calculations, you're going to make what's called an ICE table. And I did talk a little bit about this in the Le Chatelier lesson. So that is, we just quantitatively said, is it going to shift to the right? Is it going to shift to the left? Now we're going to look at what the equilibrium concentrations actually are. So when we use the acronym ICE. So I stands for initial, and the square brackets mean concentration. Which we did in the last unit, or the rates unit as well, but just in case you forget. Then, so initial concentration, how much does it change? So C. And then what is the new concentration at equilibrium? So you always have to have concentrations in an ICE table. So if you are given moles, then you need to divide by volume, which has to be in liters. So often you don't, like, it kind of depends on really how many marks you want a question to be out of. In this example, or in all of the examples, I believe, we are going to calculate what concentration is, just to review that from grade 11, but you could be given concentration as well. So if you remember the units for concentration, they can be moles per liter, but chemists are lazy, so more often we are going to use capital M, okay? So then when you have an ICE table, so the initial amount, right? So you're a scientist, you put in you know how much reactant or product you put in, and then it starts to change, and maybe you don't know quantitatively how much it's changing, and then you need to figure out what the equilibrium concentration is as well. Okay, so when we do an ICE table, you're often looking for the E line, and so what we're going to do is I plus C equals E. So whatever's in the initial line plus whatever's in the concentration line is going to equal what's at equilibrium. And that's going to help us build expressions. So this section requires quite a bit of algebra, the quadratic formula sometimes. So it's important to do the chemistry and build the ICE table, but the math here is also important as well. Okay, so the initial concentrations are changed by some factor, which we're going to figure it out, and then we figure out the new concentration at equilibrium. So if in Le Chatelier's lesson we said it shifted to the right, that would mean the product concentration in the E line or equilibrium should increase. Before we didn't say how much it increased by. Now that is what we're going to calculate. Okay, so just for problem number 1 today, we're going to do, we have 1 mole of ammonia gas and 0.4 moles of N2 gas are placed in a 5-liter container and allowed to reach equilibrium. So again, in this case, you're given moles and you're given liters, so you can calculate concentration more so that you can, so we're reviewing that from grade 11. Okay, you don't always have to do that. It is found that 0.78 so it reaches equilibrium. Okay, so initially we have 1 mole of NH3, 0.4 moles of N2, then it's equilibrium, and now it's changed to 0.78 moles of ammonia. Okay, so now we went from the initial amount up here, and now it's changed, and at equilibrium we found 0.78 moles. So we're going to use that information to figure out what the change is. And then because of stoichiometry, because we're dealing with moles, which is a relatable concept, right, due to stoich, then we can figure out how the other substances change as well. Okay, so here's the reaction. So again, just to kind of give it a double check, does it have aqueous and gas? Yep, they're all gases. There's no solids or liquids, so we're good to go. Okay, so what is the concentration in moles per liter of each species at equilibrium? So species is just a fancy word for like substance. So we're going to find the concentration, then we're going to convert it back into moles. Again, more as a review of grade 11 to make sure you're good with that. Then we are going to find the value of the equilibrium constant. So problem number 1 is unique because you're given one of the amounts at equilibrium, and that's all you need is 1. Again, when you, because it's based on moles, then we can use stoich to figure out what the other ones are. But in this case, we are not given the equilibrium constant. And how did I know that we weren't given it? Well, look, in number C, it says to calculate it. Okay? So similar to last year, in grade 11, when you had like limiting reagent or percent yield problems where you had to apply moles, I always try to encourage students, well, if you forget how to do everything else, if you at least change the grams into moles, then you'll get part marks. So the same sort of thing applies here. If you don't know how to build an ice table, you forget how to do everything else. If you changed these mole amounts into concentration, it would at least get you 3 marks. So 1, 2, 3. Okay, so I encourage you to do that. Just find the concentrations first and figure out the ice table second. Okay, so we've got ammonia's concentration initially is 1 mole over 5 liters, which is 0.2. Again, use moles per liter or big M, it doesn't matter. N2's 0.4 over 5 is 0.08. And then at equilibrium, 0.78 over 5 is 0.156. So we use all the same volume because this is like in a 5-liter closed flask or something, right? You can't change the volume because, as you guys know, if you change the volume, then that would bring into account Le Chatelier's principle as well, and then that's sort of stressing the equilibrium, and that's not what we're trying to do here. We just want to know, as is, what is going to happen with this equilibrium. Okay, so now we have concentration, and again, one more time, you're only ever going to put concentrations in an ice table. So we can go ahead and do that. Okay, so you've got the skeleton there on your sheet. I have underlined the coefficients on purpose. Okay, so we have I, C, E. So again, initial, what's the change, and what's going to happen at equilibrium. Okay, so when you do an ice table, only concentrations. So we just calculated 0.2 molar ammonia initially, and it doesn't tell us anything about hydrogen, which means then we have 0 initially, and then we have 0.08 molar ammonia or nitrogen. Okay, I'm going to put a line through that. So normally this again, I've chosen this example to be a little bit tricky on purpose so that when you go to do the other questions, it's a little bit more straightforward. Normally, both of the products will actually be 0, right? And then that's normally what you're used to. You put the reactant in and it starts to make the products. But in this case here, we've got no, I can't get rid of it. We've got a little bit of N2 to begin with. It doesn't really matter. Okay, so now we need to figure out how it's going to change. So when you have something that's unknown, the most common unknown variable is, of course, X. Okay, so how are these substances going to change? We don't know. So we're going to use the term X. And then again, like I said, you could have to do algebra, quadratic formula. So you're used to using X, so I recommend that you use X. Could you use whatever variable you wanted? Of course you could. But again, because you guys are used to X from math, whatever, then just keep with X, okay? So now we're going to find out how much it's changing by, but we also need to figure out which direction this is going to go, okay? So now, in this case, we are given the concentration of NH3 at equilibrium. So it says it's 0.156, which is less than 0.2, which means that concentration has gone down. There are going to be questions like in problem 2 and 3 that don't give you a concentration. So what do? Well, you have to apply Le Chatelier's principle, okay? And it's all based on concentration. So if you have a, let me see, I'm going to change the color, maybe, yes. If you have a, oops, sorry about that, I just did it again. If you have a substance that has 0, which means there is none of it, then you need to make more of that. So let's say we were going to say, okay, I'm going to use up the N2. Well, according to the chemistry concepts, you would also have to use up the H2, which you can't go below 0. We can't create matter from nothing. That doesn't make any sense. So we can't go in the reverse direction or left. So when you're doing these types of problems, whatever direction has the 0, you have to go up from 0. You can't go below 0. So this equilibrium has to shift to the right. Okay, so I wrote B/C there because I was squishing. So that means because. So you're going to shift to the right to make H2 because its concentration starts at 0. Oh, there it is down there. So the reactants are decreasing, so their change is going to be negative, and the products are increasing, so their change is going to be positive. And again, if you wrote an expression like 0 minus 2x for when you're talking about concentration, you can't go down from 0. So wherever the side is that has the 0, it's going to shift that way. Okay? So, oh no. Okay. So when that means that this is going to be a negative and these two will be positives. Okay, and so again, I said I underline these coefficients, and I did that on purpose because you do have to obey stoichiometry. So every time a reaction occurs, we're going to have two ammonias used, and then you're going to make 3 moles of H2 and only 1 mole of N2. So you want to make sure you take that coefficient into account. So how much is the NH2 going to go by? Down by, it's going to go down by 2x. How much is the H2 going to go up by? It's going to go up by 3x. And how much is the N2 going to increase by? It's going to increase by x. Okay? Okay, so now somewhere on your paper, don't write in the E line here, like don't write in here yet, but somewhere on your paper, remind yourself okay, I plus C equals E. Okay, so I'm going to start on the right here just to cheat. So we have, if we do N2 first, we have 0.08 plus X. H2, 0 plus 3X. Okay, and then the last one is a unique. Again, this is a unique problem because because problem 1 is unique because we do know something at equilibrium. So here we have 0.2 minus 2x. And why did I put minus there? So again, back to the math side of things. If you do, where can I write it? Let's say you do 0.2 plus negative 2x. What do you get? Oh, it changes into that. So you can certainly write it like what's in the brackets if you want, if that makes more sense to you. But when you add a negative, it just becomes like subtract. So it doesn't matter. So now there are really two basic types of problems. Either you get a line like this in your ICE table where the x, there's no known value of the at equilibrium, which means that you have to be given a KEQ value. That's problem 2 and 3. But this time we do know what NH3 is at equilibrium. What is it? Oh, let's just go back here for a second. There it is, 0.156. Okay, so we do know what it is at equilibrium. So we can use that in our ICE table. Okay, and now we have this little expression here that we can use to solve for x. So when you know one of the concentrations at equilibrium, you can easily solve for x. So this comes from the E line. Why NH3? Again, because we're given its concentration at equilibrium. I could have just as easily given you some other concentration, but I chose not to for whatever reason. So just make sure you read the question carefully. Back in the original question, it said, it is found that 0.78 moles of NH3 is present after it reaches equilibrium. Okay, so we're going to use that E line and we're going to solve for x. So you can decide for yourself how much work you need to show. Okay, so bring the number to the other side, subtract, divide by -2, and you get 0.022. When you do these questions, something that's very important is, again, you know, to ensure that you get all the marks possible, is that this is actually you're not done. We haven't even answered A yet. Okay, so we need to answer A, which means we need to take the x and make sure that we've answered the question. And no matter what kind of problem you do, whenever you solve for x, you're always going to want to go back and sub it in. So this question says, what are the concentrations at equilibrium? And so we're going to go to the E line. So we have 0 plus 3x in H2's in the ice table for H2. Some people will choose to right underneath their ice table fill in the value. That's fine, it doesn't matter. I chose to keep the 0 here just to emphasize the I plus C equals E. If you, obviously the 0 doesn't change the math, like you moving on, you don't need to do that. Okay, so then we have 3 times 0.022, which makes 0.066 molar. And then N2 is 0.08 plus X. So 0.08 plus 0.22 molar makes 0.12. Part B says find the number of moles. So now we're just rearranging the triangle essentially from grade 11. So 0.66 times 5 is 0.33 moles left. And again, so we shifted to the right. So we started with 0 for H2, so it went up. Does that make sense? Yes, right? It shifted to the right in order to make more. Same thing with N2. We started with 0.4 moles in the question. It went up to 0.51. So now we basically, again, we've proven Le Chatelier's principle. We saw it shift to the right because it needed to increase the concentration and balance out. And what is the value of the equilibrium constant? So if you remember from 7.2, you have to make sure that you write this out, okay? So please make sure you write out the equilibrium law if you would like to get full marks. And then you're just plugging in the numbers and making sure to follow BEDMAS. You do the cubing and the squaring before you multiply. And these numbers, again, just come from the coefficients. And it's always products over reactants. Okay? Okay, so we're going to stop there, and I encourage you to do the homework assigned for this first and get the problem number 1 type of problems out of the way, and then I will post another video for problem 2 and 3. I'm going to also, if this was in class, we would do quizzes. So I'll post a quiz and then I'll post a solution so you can mark it for yourself and see how you would do, basically assess yourself. Usually there's a huge unit test for equilibrium, and just based on the nature of what's going on, eventually I think we'll just have an introduction to equilibrium assignment. Okay, so doing the quiz and assessing yourself is a good way to know if you're on the right track. Please, if you have any questions, let me know. Thank you.